Okay, so we talked about elongation and contraction due to tension or compression. So now we're going to talk about elongation due to temperature change. So this is thermal expansion. And the formula we're going to use is that the elongation, I'll call it T for thermal or temperature, is equal to the coefficient of thermal expansion, alpha, not the angular acceleration, times the length before the deformation, times the change in temperature. And this coefficient of thermal expansion is something you can just look up. You know, you can Google it or whatever for the material. What are the units of the coefficient of thermal expansion? Anybody know?
Length. Is it 1 over temperature?
Yeah, good job. I was just about to go through that. So if you're ever, because I looked at that and was like, oh yeah, what are the units of that? Well, so you can always, any constant that you have in an equation, you can always figure out the units of it by just thinking of the units of everything else and then just solving the equation. You know what I mean? So like, what are the units of alpha? You could think of this as this elongation is going to be meters, and that's equal to alpha times length is meters. This is going to be Kelvin. And so now solve for alpha. The meters cancel, and alpha is equal to 1 over Kelvin. Or 1 over degrees Celsius. For the people who took thermo already, you're pretty familiar with this thing. Remember that, so temperature is a weird unit. Compared to every other unit that we use, temperature is weird, and it's because not all temperature scales have the same 0 point. Every other unit has the same 0 point. You know, 0 meters is equal to 0 inches. But temperature is not that way. And so the for actual instantaneous temperatures, the Kelvin temperature is the Celsius temperature minus 273.15. Okay. But for changes in temperature, the change in Kelvin is the same as the change in Celsius. Okay. And that works because that works because a a change, you're subtracting two temperatures, and basically you're subtracting, so you're subtracting that constant at 273 out, and it disappears. Okay, so
Shouldn't it be plus 273.15?
I was just trying to think of that.
0 Kelvin,
0 Kelvin,
negative 273 Celsius, plus that amount.
0 Celsius
Yeah,
is,
so
yes,
0 Kelvin.
thank you, yes.
Absolutely.
Yeah, I was, yeah. Thank you.
But it's different for Fahrenheit because that changes at a different rate.
Right, correct.
You don't
Unless you're giving it in Rankine.
Yes. All of those statements are true. We'll just do everything in Celsius. I don't want to make a big deal out of this, but just notice that temperature is always like your spidey sense should tingle when you're doing calculations with temperature, because like any kind of unit conversions or anything, because that additive constant makes everything weird compared to what you're used to with every other kind of unit, you know. Be extra careful, basically. So if the temperature increases, that leads to elongation. When we eventually get Elon Musk on one of those stretching machines, those torture devices, that's what it's going to be called. That was a good snort.
For that, I was like, he's got his name in that.
And the temperature being reduced leads to contraction. Sometimes it can be a little confusing about what happens to complicated shapes as the length changes. Notice that this is valid for any length dimension. So for example, if you start out with a torus donut shape and take this measurement, and then you increase the temperature, like this measurement here, will it increase or decrease? You know, you might sort of think like, oh, you can get yourself kind of confused, like, oh, well, the length is going to increase, and maybe that squeezes more material into the middle and maybe reduces that. But that's a length dimension, that's a length measurement you can take, and so it's going to increase, and that's the end of it. Okay. What?
It's a lot of thermal expansion.
Yeah, that's a big one. That material has a very big solid range. Okay, so let's say that we have a beam or a bar with two cross-sectional dimensions. And let's say, so we're going to apply a horizontal force of 5,000 newtons here and 8,000 newtons here. And the cross-sectional area for this part is 0.01 meters squared. And the cross-sectional area for the other part is 0.003 meters squared. And let's say that the length of this piece is 0.4 meters and the other one is 0.3 meters. And let's say that we know that the Young's modulus is 110 times 10 to the 9, that's copper. And the coefficient of thermal expansion is 1.0 times 10 to the minus fifth. I don't know if that's copper, but metals are somewhere in that range. And the temperature is increased 100 degrees Celsius. What's the elongation? Oh, by the way, you know how if you put a cold glass dish in a already heated oven, it'll crack? That is because of this thermal effect, and it's because the different parts of the glass will heat up at maybe slightly, but they'll heat up at different rates. And so the thermal expansion happens in different places in the dish at different times, and that mismatch in sizes leads to cracking. So if you wanted to make a kind of glass that was less susceptible to cracking in lab conditions or in ovens or whatever, you would want a smaller coefficient of thermal expansion, so there's less difference, less size mismatch for the same amount of temperature. And that's what Pyrex glass is. It's just basically glass that they've figured out how to lower the coefficient of thermal expansion on. And that's why it's useful for lab flasks and why it's useful for casserole dishes. Okay, so what we're going to do is, like we always do with this stuff, we're going to break it up into two pieces and use the principle of superposition. So I'll start with the results of the tensions. So we have to calculate those internal tensions, and that means first we have to calculate the external tension. So I'll call this R. We have a force here of 5,000, a force here of 8,000. Newton's second law in the x direction says R plus 5,000 plus 8,000 is equal to 0, and so R is equal to negative 13,000 newtons. And now we can do our cuts. So cut 1 is for the fat part. That's from x equals 0 to 0.4. We have 13,000 going this way, t this way. So Newton's second law says negative 13,000 plus t is equal to 0. So the internal tension for the first part is positive 13,000. And then for cut 2, this is valid from 0.4 to 0.7. We have 13,000, 5,000, right, say 5 and write an 8, 5,000, and then t. And so Newton's second law in the x direction says negative 13,000 plus 5,000 plus t is equal to 0. So T is equal to 8,000. And now we'll use the sum formula for the elongation. So the elongation is, it's the sum of TL over EA for all the parts where all that stuff is piecewise constant. So I'll write it as T1 L1 over E times A1, just because the E is the same for both of them, plus T2 L2 over E times A2. And so that is 13,000 times 0.4 over 110 times 10 to the 9 times 0.01 plus 8,000 times 0.3 over 110 times 10 to the 9 times 0.003, and you get a value of 1.2 times 10 to the minus 5 meters. Okay, so if there was no temperature change, this would be the elongation due to those tensions. And now we're going to act like those tensions don't exist and just figure out the elongation due to the temperature change, and then we'll just add those two together, superposition principle. Okay, so now we'll go to the thermal. And the elongation due to thermal expansion is equal to the coefficient of thermal expansion times the length, which is 0.7. We don't have to break this up into areas or anything because the area doesn't come into the formula. Times the change in temperature. We're using SI units. This increased 100, so this is plus 100. If it decreased, it would be negative. And we get 70.0 times 10 to the minus 5 meters.
Is it actually like pretty linear like that?
Yeah. And then, I mean, 100 degrees is a big temperature change for a solid, you know. I mean, it has to start pretty cold for something to still be solid. Either it has to start pretty cold or at a pretty high pressure, or a combination of the two, to still be a solid after you increase it 100 degrees, you know. And then after the phase change, there's still thermal expansion, but a liquid doesn't have any kind of, so a solid has length dimensions, like undeformed length dimensions. And so the thermal expansion equation deals with those length dimensions. A liquid doesn't have undeformed length dimensions. It'll take whatever shape of the vessel it's in. And so you go to a thermal expansion equation that deals with volume change. And then once you phase change from a liquid to a gas, well, a gas doesn't have an intrinsic volume. It'll expand to whatever volume you give it. And so the gaseous form of thermal expansion is the ideal gas law. Okay, so now put these two together. and the total elongation is the elongation due to the tension compression plus the thermal elongation, and it is 71.2 times 10 to the minus fifth meters.
Crazy how much more the thermal expansion was.
Yeah, well, that's a really big temperature change. But yeah, you can get, I mean, we'll see when we start getting into statically indeterminate structures. Like there's a lot of potential for using thermal expansion to generate big forces, you know?
Like intentionally.
Yeah, right.
Why do we only calculate thermal in the x direction?
Because that's all I was trying to, that, if I didn't say it explicitly, I mean, that's all I was trying to do is figure out what the elongation was in the x direction.
I'm sure you can take it for any length and
Yeah.
cross-sectional area depending on the
Yeah,
temperature.
although things would get weird in this case, you'd have to like, okay, give me more details about how this is attached to the wall, you know? Because like, if that wall keeps this, then it would have some sort of like weird bulbous shape, and you'd have to think about St. Venant's principle and stuff like that. But for just doing the elongation, it's easy. I have another question while we're talking about that St. Venant's principle and stuff. So when we were talking about stresses in beams, one of the things I said was you have to be careful. We can treat, so these are kind of drawn as point forces. We sort of make the assumption that everything's happening uniformly, so we'll really assume that this 5,000 Newton meters is distributed uniformly over that whole area, and then this is distributed evenly over that whole area, and this is distributed evenly over that whole area. Well, St. Venant's principle says it's okay to make that assumption as long as you move away from those loaded faces before you make that assumption. But now we're including those loaded faces in this calculation, you know, because we're talking about the elongation over the whole thing. So is there anything weird about that? Well, as long as the length is a lot greater than the, you know, I haven't drawn it like the length is super big, but with the dimensions I gave, this length is a lot bigger than those cross-sectional dimensions. And so we're only talking about a very small distance from like the wall into the body. And here we're talking about a very small distance. And here we're talking about a small distance. And so those are going to be small contributors to the overall macroscopic elongation. And so we're just always going to assume that those are getting kind of swamped out by the rest of the elongation that's happening in the bulk of the material.
Is it only the tension that contributes to the length change?
Yes. And, you know, and the temperature change.
Right. I guess I'm just mad, like, if you like bent something, like one
Mhm.
side gets longer and the other side gets shorter, right?
Right.
But I suppose like the
At the neutral axis or whatever.
Same.
Yeah, right.
the neutral zone.
Yeah. Okay, so now we're going to use this with statically indeterminate systems. This is our first statically indeterminate system.
That's so exciting.
I know.
And someone told me that like you couldn't solve for one of those, like the really simple ones.
You just punched him in the face.
I just laughed and said, "You're an idiot." No, it just
Yeah.
seems so crazy to me.
Yeah, exactly, yeah.
You know, it's like something so simple.
Right. Well, I mean, so what it really is that you just need to know about the nature of the deformation before you have enough information to solve for it, you know. So I like to think of this in sort of two steps. The first one is do the statics. As these things get more complicated, it's not obvious immediately often, like whether something's statically determinate or not, you know? So do the statics. look at your equations, count the variables, and if they're the same number, it's statically determinate. If it's not, then you know you have more to do, you know? So the first step is do the statics. If you have more variables than useful equations, it's statically indeterminate. And so then, you know, just set those equations aside for later. We're just going to have to solve it as a big system. And now second, we're going to use the displacement equations. To come up with the necessary geometric constraint equations. And then I guess if you could call it step 3, you're just going to solve this system of equations. Okay, so let's say we have this bar that's fixed at the top and bottom. It's 1 meter long. And a quarter of the way up, a force is applied downward of 20,000 newtons. And let's say that the cross-sectional area is 0.01 meters squared. What are the reaction forces, the reactions at the top and the bottom? Okay, well, this is, at first glance, this is as easy as statics can get, you know. It's just a one-dimensional Newton's second law application. So the free body diagram looks like this. I'm going to put my reaction forces in the positive y direction. So I'll call this RA, RB, and then this downward force of 20,000 newtons. And now, you know, you get an inkling that there's a problem. Newton's second law in the y direction says RA minus 20,000 plus RB is equal to 0. And so we have, okay, so there you go. Now it's statically indeterminate because we have 2 variables, only 1 equation. And so I'm going to set this equation aside for later. I'll put it in the form RA plus RB is equal to 20,000. and I'll call that equation star. And so now we're going to use the elongation equations to come up with geometric constraints. And our geometric constraint, I mean, the basic idea of it is going to be that the total elongation of this thing has to be 0. We're going to assume that the floor and ceiling can't go anywhere, you know? And so whatever happens, this point and this point have to stay 1 meter apart. Okay. So now I'm going to do the cuts because we have to calculate those internal loads in order to use the elongation equation. So cut 1 is for, I'm going to flip this on its side because we're used to doing internal loads that way. And I'm going to do it with the floor on the left. So this is for x's from 0 to 0.25. So my RA is this way. And my internal tension is this. Newton's second law says RA plus T is equal to 0. So T on this cut is equal to negative RA. Okay. And now I'll go to cut 2. This is for x's between 0.25 and 1. We have RA here. We have 20,000 this way. And an internal tension T. Newton's second law says RA minus 20,000 plus T is equal to 0. So our internal tension in this case is negative RA plus 20,000. And now our constraint equation is going to come from that elongation expression. So the constraint is going to be that D total is equal to 0. Okay, so our expression for delta total is the tension on the first piece, and we figured out that that's negative RA, times the length of the first piece, which is 0.25, divided by, I didn't give E, I did give A. It turns out it's not going to matter because it's the same for both of them. That's the elongation on that first cut. The elongation for that second cut is negative RA plus 20,000 times the length of 0.75 divided by E times 0.01. And we're setting this equal to 0. Well, you can multiply both sides by 0.01 E, and the denominators cancel. And so we get negative 0.25 RA minus 0.75 RA plus 15,000. is equal to 0. So RA is equal to 15,000. I guess you might want to, I don't know. This is our, equation 2 star for our system of equations. Our RA is 15,000. Now we can go back up to equation 1 star. We know that they add up to 20,000. So this and equation star together tell us that RB is 5,000.
Pretty neat. So
Yeah.
is this how we do for these problems? We don't then go and calculate the deformations?
Well, in this case, the deformation is 0, but there are problems where I would say, like, what's the displacement of the point at the center or something, Okay, one thing that we will see pretty often, and I think there's a problem like this on the assignment I'm going to give you, is let's say that we have what we're going to assume is a relatively rigid bar, and it's being supported by 2 cables. Okay, and let's say that we have some force acting down of let's say 1,000. Let's say that this is 1 meter, this is 1 meter. We're going to assume that this bar is a lot more rigid than those cables, okay? And I'm going to give you an effective area of the cable of, I don't know a value for that, but let's say 0.002 meters squared, okay? And we're going to say that the Young's modulus for the material on the left is 200 times 10 to the 9. And the Young's modulus for the one on the right is 100 times 10 to the 9. And we want to know what are the tensions in those 2 cables. Okay, so what we're going to do is assume that the bar is rigid. It's a lot more of a challenge getting this thing in the calibration thing now with my stupid broken pencil.
How'd you break it?
I was just in the middle of class and the top popped off. It was just
like
the 50,000 loading cycle I get, or whatever, you know what I mean? Like eventually it just breaks. Oh no, it didn't calibrate, this stupid thing. Get in there, you dirty motherfucker.
Can we calculate the material weakening of those 50,000 cycles?
Yeah,
See if we can't calculate.
we should. That would be a good class project. I don't remember which direction this goes.
The RIV.
went in there. Come on, baby.
Wait and see flash light.
Yeah. Yay. Okay, so I'm going to assume that the bar is rigid. And that means that the deformations of these two things have to be along a line. Okay, so I'm going to exaggerate this, but we're going to assume that we have a right triangle. Okay, and this is like, so this is the distance the end goes down. You know? This distance here is 1 meter. This distance is 1 meter. And so what we have to have is similar triangles. So I guess what matters here isn't this exactly. It's really the fact that this one is 1 and this one is 2. Okay, so I'll call this L1 and L2. And those are similar triangles, you see that? And so what we have is that L1 over 1 has to be equal to L2 over 2. And so L2 has to be equal to 2L1. You with me on that? It's just similar triangles. And so that's going to be our constraint equation. It's going to come from that. Okay. Well, let's go through the steps. So first we'll do the statics. So a free body diagram of the, I'm going to do a free body diagram of the bar. We have this force R over here, and we have tensions here and here. I'll call this T1 and T2. And then we have this downward force of 1,000. We could do Newton's second law. It'll just give us a relationship between R and T. It won't end up helping us. But let's go to the moment equation. And with our about point over here. So we have that 1, the moment arm of 1 times T1, plus the moment arm of this T2 force, 2 times T2, minus 2 times 1,000 is equal to 0. So we have T1 plus 2T2 is equal to 2,000. I'll call that my equation star, and now we know that it's statically indeterminate. If we wanted, we could have left the Newton's second law equations in there. Instead of one equation for 2 variables, we would just have 4 equations for 3 equations for 4 variables, because we'd get the additional variables of Rx and Ry. So now we'll go to the constraint equations. Yikes. And so now we're going to say that the elongation of the one on the left I guess the way I wrote it is the elongation of the one on the right has to be twice the elongation of the one on the left. Okay? And so now we'll plug this stuff in. D1 is T1 times its original length, which I didn't give. Is this going to matter? I don't think it's going to matter. I think because we assume that they start with the same length. So I'm just going to call them both L for the length. Divided by this one, we have 200 times 10 to the 9 and an effective area of 0.002. Our delta 2 is T2 times that same starting length divided by 100 times 10 to the 9 times 0.002. And now our constraint equation says T2 times L over 100 times 10 to the 9 times 0.002 is equal to 2 times T1 times L over 200 times 10 to the 9 times 0.002. And we can cancel a bunch of stuff. This cancels, this cancels. Well, this answer is going to end up looking boring because I happen to pick values so that this and this canceled the 1 and this. But it doesn't always do that. That was just because I happened to make the ratio of the E values exactly the same as the ratios of the distance from the about point. And so we get, and the L's cancel. And so we get T1 is equal to T2. And that's our equation 2 star. And now we can solve that system. We know that, so basically 3T1 is equal to 2,000. So T1 is equal to 666.6 repeating, and that's also equal to T2.
Such an evil problem.
Yeah, exactly. And if I had made those the same material, then, they would have there would be different loads in the different cables. Okay, so I'm definitely, I think, giving you an assignment problem like that. All right, goodbye.